Shortly, we're going to learn to interpret the areas under the normal curve, and we're going to do that in order to make some statistical estimates of what can happen in certain, I think, fairly interesting situations. And this is something that's extremely important in a lot of applications, both in science and in business and in the social sciences and so forth. Now, to interpret the area under the curve, we ask the question, what's the area between the center, where z equals 0, and some z value out here? How much area is there? How much of the area under the curve lies between 0 and a given z value? Your textbook has a table here. Now, you're not going to be able to see the details of the table, but you see a picture very much like the one that I drew. This one's more accurate than the one I drew. I didn't quite get the shape right. But what you have here, and you can of course look at this in your textbook, is you have z values going down this column and areas going down this column. And then you have some more z values and some more areas and so forth. The z values go from 0 to 0.01 to 0.02. In the first column they go all the way down to 0.55, and you can't see the bottom of the column. In the last column, going by 1/100th at a time, we go all the way up to z equals 3.33 at the bottom of this column. And we see what the areas do. Now, you can't read those, but if you look in your book, you'll see that these areas, as we go up to z equals 3.33, approach 1/2, 0.500. They start at 0, the first area. The area for z equals 0 is 0. The area for z equals 0.22 is 0.87. The 34% that I mentioned would correspond to z equals 1. Now, that's down, it's in this column, just a little bit below where you can see, and it's 0.341. You can check that. Look under z equals 1, you get 0.341, which corresponds to that 34%. So the table is going to tell you, if you give it a z value, it's going to tell you how much of the area you've got here. As z approaches bigger and bigger numbers, the biggest number in the table is 3.33, you'll see that to 3 decimal places, all the area is under here. Now, if you went out to 4, 5, 6, 7, 8 decimal places, it wouldn't be exactly 1/2. But we can see that as we go further and further out here, if z moves from here over to here over to here, this area is going to incorporate more and more of the curve. And as we move to the right, it's going to get closer and closer to being half of the curve, which is the 0.500. So again, the table is telling us the proportion of the total area that lies between 0 and z. We can answer important questions this way. For example, suppose that we have a situation that we saw before, a mean of 85 and a standard deviation of 3.4. Now, remember, that was the original example of a test where we had a mean of 85 and a standard deviation of 3.4. If we had a test with these characteristics, how many out of 200 people would score more than 90? And let's say that 90 is a cutoff for an A, so we're asking how many A's you would expect. How many would score more than 90 on such a test? Remember that you scored 90 on that test, right? In order to solve that, we calculate the z-score. Remember, we calculated the z-score. You were 5 units above the standard deviation and the standard above the mean, I'm sorry. Because the mean was 85 and you made 90, you're at +5 on the raw scale. Standard deviation is 3.4, which puts you at approximately 1.5 on the z distribution, the z-score. So the z value of your score is 1.5. That means that your 1.5 standard deviation is better than the mean. Okay, and that's the z for 90. Now, if we look at the table, and if we look at z equals 1.5, the table is going to tell us what the area is between the middle and z equals 1.5. And it tells us, in fact, that that area is 0.326. Okay, so 32.6% of the total area under the curve, and you know, that just isn't right. I'm going to have to look that up. Excuse me a minute. Okay, I misread the table, unfortunately. I'm thinking about what I'm doing now, where I was just reading numbers before. If we come down to 1.50 for the z-score, I read to the left with 0.326, but it's really 0.433. Now you can't see what I'm doing, but I'm coming down to 1.5 under the z, and I'm looking at the corresponding area. And I looked the wrong way when I did that. If I'd been thinking, I would have known that between 0 and z equals 1 is 34%, and this is only 32%. So that 0.326 is wrong. That should be 0.433. So that instead of the 0.326, we're going to say 0.433 of the distribution of the scores are going to lie between 85 and 90. Now, we also see that 50% of the scores lie below the mean, so that this 43 1/3% here lie below z equals 1.5. If we want all the scores below 90, okay, we would take that 43 1/3% and add the 50% here, and see that 93.3% of all the scores lie below 90. Now we're going to go on with this example in a minute, but I'm going to take the opportunity to stop this clip and make a couple of corrections because of my misreading of the table here.